Yes, can all of you hear me? Okay, perfect. So last time we finished our amines, right? Last time we finished our amines, amine chapter completed, right? Okay. So today I'm going to start with the biomolecule. Next chapter we have biomolecules. I'm sharing my screen with you. Just a second, please. Let me switch on the one turn on. Yeah, just a second. Yeah. Can you see my screen, everyone? Please speak out.
Yes, sir.
Right, right. When I talk about the word biomolecule, this chapter, it is made up of two components, two words. One is the bio, other is the molecule. Bio means something living, bios, life. And molecule we know molecule, chemistry. Those molecules which are responsible for growth, maintenance, survival, and reproduction of any organism is called as a biomolecule. See, those molecules which are responsible for survival, growth, reproduction, those molecules are called biomolecule. These molecules are carbohydrate, proteins, enzymes, nucleic acid, lipids, fats, all these are biomolecules. Without them, life is not possible. So we call them biomolecules. And the study of these molecules is technically called as biochemistry. So we have a separate branch of chemistry that deals with the study of biomolecules. Their role in the living organism is called as a biochemistry. Right. So I'll be discussing one by one. In our syllabus, we have carbohydrate in detail. We have proteins in detail and nucleic acid. Only these three are there in our syllabus. Rest are not in our syllabus. So we'll not go for that in detail. We'll go for only these compounds in detail. Right? Today and next class, it will be taking two classes. It's lengthy chapter. Carbohydrates takes a lot of time. So I'll go for by carbohydrate first. So what are carbohydrates? Carbohydrates are those compounds which are hydrates of carbon. This is an old definition. hydrates of carbon is called as a carbohydrate. Hydrates of carbon is called carbohydrate. For example, if I say C6H12O6, it's glucose. So I can say C6 and H2O6. It's a hydrate of carbon. It is a hydrate of carbon, right? It is a hydrate of carbon. We can say it's a carbohydrate. Similarly, if I say I have a sucrose C12H22O11, it is sucrose. I can represent this molecule C12H2O 11 times. So it's a hydrate of carbon. This was the old definition, but this definition was later on proved wrong. There are some molecules which are carbohydrate. For example, if I say rhamnose, C6H12O6, rhamnose, C6H12O5, this is rhamnose. This is a carbohydrate, but not hydrate of carbon. It is not hydrate of carbon. So we cannot represent this as a hydrate of carbon. We cannot represent this as a hydrate of carbon. Understood? This is a carbohydrate, but practically it's a carbohydrate. But theoretically, we cannot represent the molecule as a hydrate of carbon. We have a deoxyribose. Deoxyribose. This formula is C5H10O2. This is a carbohydrate, but it is not a hydrate of the carbon. Even though these are the carbohydrates, but these are not hydrate of carbon. So this is against the definition. Another, I have some compound like formaldehyde, HCHO, CH2O. It's a hydrate of the carbon, but the formaldehyde is not a carbohydrate. Formaldehyde is not a carbohydrate, right? It is not a carbohydrate. It is a hydrate of carbon, but not carbohydrate. Even though it's a hydrate of the carbon, it means it fits into the definition, but it is not a carbohydrate. Similarly, we have an acetic acid. You can see CH3COOH. It's a C2 and H2O whole twice. It is not carbohydrate. It is not a carbohydrate. Understood now? It is not carbohydrate. So a new definition was given about the carbohydrates. Read on that definition. Carbohydrates are optically active. Polyhydroxy, aldehyde or ketones, or the compounds which produce such compounds on hydrolysis is called as a carbohydrate. Is called as a carbohydrate. So carbohydrates are those compounds which are number one optically active. When I say optically active means that must have some chiral carbon atoms. Polyhydroxy means more than two OH group. It may be aldehyde or a or it may be ketone, RCOR, ketone. Or those compounds which produce upon hydrolysis are called as a carbohydrate. For example, and I'll give you one example here. If I say the structure of glucose, C6H12O6, 1, 2, 3, 4, 5, and 6. I'm drawing the structure of carbohydrate. Right? You can see this is a chiral carbon atom. This is a chiral carbon atom. This is a chiral carbon atom. There are four chiral carbon atoms. Chiral carbon atom means which are bonded to four different atoms or group of atoms. These are called as the chiral carbon atoms. These are polyhydroxy. You can see more than one, more than two OH group are there. Polyhydroxy. And it is a aldehyde group. You can say it's aldehyde group. It is a polyhydroxy aldehyde. Right? It can be aldehyde. Polyhydroxy optically active. Now another structure that I'm drawing here is of the fructose. Its formula is also C6H12O6, same molecular formula. 1, 2, 3, 4, 5, and 6. But here we have a ketonic group. Right? It's a fructose. It's a ketonic group. It's a polyhydroxy. And this is a chiral carbon atom. There are three chiral carbon atoms here. This compound is called as the fructose. Fructose are those compounds which it's a carbohydrate, right? Fructose is a carbohydrate. It's a ketone, polyhydroxy, and it's optically active. Right? Glucose is also like that. It is an aldehyde. So such type of compounds are called as a carbohydrates. Am I clear now? Now we discuss about the classification of carbohydrates. Classification of carbohydrates. We can classify it a number of ways. One way is sugar and non-sugar. Sugar are sweet, water soluble. Example: glucose, fructose, cane sugar. Right? These are sugar. And non-sugar are those which are tasteless. insoluble in water. These are amorphous. For example, starch, cellulose. These are non-sugar. So we can classify them as sugar and non-sugar. Next one. The further classified as the further classified as monosaccharides. Monosaccharides are those which cannot be further hydrolyzed. Which cannot be further hydrolyzed. These are simplest one, right? For example, if I say we have a glucose, we have fructose. These are the monosaccharides. They cannot be further broken down into simple carbohydrates. But if I say I have some disaccharide, upon hydrolysis, it will give two simple carbohydrates. It will give two simple carbohydrates. For example, I say sucrose. If I hydrolyze it, add water in the acidic medium, it will give glucose and fructose. So it is giving two simple carbohydrates, and that is why these are called as a disaccharides. Am I clear? Next we have a trisaccharides, which upon hydrolysis gives three simple carbohydrates. Right? For example, we have a raffinose. If you go for the hydrolysis, it will give three simple carbohydrates. It will give mannose, fructose, glucose. Similarly, we can have tetrasaccharide and we call it a polysaccharide. So, depending upon the number of the carbohydrate they provide, they are further classified as a monosaccharide, disaccharide, trisaccharide, right, and so on. Now, we'll go in detail about the monosaccharide first. Monosaccharides are those which have some aldehyde. We call them as an aldoses. Ketone group, we call them as a ketosis. Right? Those compounds which contain aldehyde group are called as the aldoses, which contain ketonic group, these are called the ketosis. Right? Now, these aldoses, we'll talk about the aldoses. If it is made up of three carbon chain only, like this, CH2, OH, CH, OH, and CHO. Right? This is known as a glyceraldehyde. And it is having three carbon chains. So we call this is a aldotrioses. Aldotrioses. Am I clear? Aldotrioses. ketotriosis. Then we can have aldotetrosis, 4 carbon chain. Aldehyde group is here, but now 4 carbon chain. 1, 2, 3, 4. Right? OH here. So we call this as a aldotetrosis. For example, we have an erythrose. We have 3 O's. Right? So depending upon the carbon atom that it has, it can be classified further. Aldotriosis. Triosis means 3 carbon chain. Aldotetrosis made up of 4 carbon chain. Aldopentosis made up of the 5 carbon chain. Right? And so on. So we call it as aldosis. Similarly, if I talk about aldohexosis, it means it is having 6 carbon chain with the aldehyde group. It means we are talking about a glucose. The structure we have done earlier. This one is the glucose molecule. I can say it's a aldohexosis. Understood? Similarly, the ketones are further classified as a ketotriosis. Ketotriosis means it's a ketonic group right? It's a ketotriosis. Ketotriosis. Similarly, if it is made of 4 carbon chain, it will be called as a ketotetrosis, ketopentosis. And fructose is nothing but a ketohexosis. Ketohexosis. Understood? Now, we are going to discuss about in detail the structure of glucose. Structure of glucose. Structure of glucose. The structure that we have discussed, I'll be proving there that that structure has aldehyde group, that structure has 5 OH group. This molecule has either the straight chain or cyclic, whatever the structure we have. Right? We have to go into detail of all this. So how do we come to know that this is a particular structure of the glucose? Right? So this is the structure of glucose. How do we come to know? Practically. First of all, we determine their molecular formula. And we know how to calculate the molecular formula. We can get the molecular formula by, like, first we find the percentage, and from the percentage we find the empirical formula and then the molecular formula. From there we get C6H12O6. C6H12O6. This is a molecular formula. And now, if this is glucose molecular formula, right? And this glucose, if it is treated with a hydrogen iodide, we get N-hexane. N-hexane is a straight chain. N-hexane is a straight chain carbon. Right? If it is a straight chain carbon, that clearly indicates that glucose must be straight chain. So I say the molecule is a straight chain molecule. Because this is a reduction. And upon the reduction, we are getting a straight chain hexane, and this proves that molecule is a straight chain molecule. Right, it's a straight chain molecule. Then we are proving here the presence of the 5 OH groups. In the molecule, we have 5 OH group. How do you prove that it is 5 OH group? Let us see. I have drawn the structure here like this. I'll redraw it. On the third carbon atom, the OH group is on the left hand side and rest all on the right hand side. 1, 2, 3, 4, 5, and now the 6th. If it is treated with acetic anhydride, if it is treated with the acetic anhydride, this H positive ion combines with the acetic acid at the 5 positions 1, 2, 3, 4, 5, 5, right? I'll be using a 5 molecules here, and I will get a 5 mole of the acetic acid and 1, 2, 3, 4, 5. At this position, I will have now COCH3. H this side, O, CO, CS3. O, CO, CS3. H, H, O, CO, CS3. And so on. So this 5 mole of the acetic acid, when it is produced, we can neutralize it by the sodium hydroxide. Then there I need 5 mole of NaOH. It means the molecule contain 5 OH groups. Am I clear till now? I'm stopping sharing for some time. Let me know. Am I clear to all? Write in the chat. All clear? If it is really clear to all, everyone. Right, Anmol. Ashwin, Vipin. Okay. Okay, perfect. If you find any difficulty, just let me know. We'll go into detail of it. Wait a minute, please. Where it is gone? Yeah. Now, we'll prove here the presence of the aldehyde group. Presence of aldehyde group. 1, 2, 3, 4, 5, and 6. I'm drawing the structure of the glucose again. You keep on drawing all these structures. It will be very, very clear to understand. If it is treated with a HCN, this HCN will attack upon the aldehyde group here, causing electromagnetic effect, and it will form the OH group here and the CN group here. Rest structure is same, right? Hydrocyanin is formed. Hydrocyanin is formed. Glucose cyanohydrin. It is called the glucose cyanohydrin. Just like the glucose, in the aldehyde cases, we have discussed this property. That is The presence of aldehyde. If you add here HCN, that forms a cyanohydrin, it confirms the presence of the aldehyde group. Rest, this whole structure is same. This whole structure is same here that you can draw here. Only the attack is going on the aldehyde group. Another, I have a aldehyde group here, right? Rest is the structure below as such. If you treat this glucose molecule with a hydroxylamine, it's an ammonia derivative. Water will go from here and oxime will be formed here. Rest structure is all same and we call this the glucose oxime. It will be called as the glucose oxime. Next we have, if you go for the oxidation of glucose, CH, OH 4 times, right? I'm writing like this 4 times. If you go for the oxidation in the presence of the bromine water acts like a good oxidizing agent. Then what happens here, the aldehyde group gets converted into the carboxylic acid. This compound is called as the gluconic acid. This compound is called as a gluconic acid. Aldehyde group gets converted into carboxylic acid. That indicates the presence of the aldehyde group. Similarly, in the chapter of the aldehyde ketones, we have discussed two conformity tests of the aldehyde ketones. One is the tolerance reagent test, other is the failing solution test. Those tests are also proved by the glucose molecules. Let us go into detail of this now. It is CHO group. Then we have CH OH whole twice with CH2OH. Treated with the tolerance reagent AG NH3 whole twice, right? Plus OH negative ion. This is called as a tolerance reagent. What it does is it converts the aldehyde into carboxylic acid. And silver mirror is formed. Silver mirror is formed. And this silver mirror formation along the side of the test tube indicates that the molecule has an aldehyde group. Has an aldehyde group. And another is a failing solution test. It gives red PPT. It gives red precipitate. And it clearly indicates that this aldehyde group is converted into carboxylic acid. Clearly indicates that right into carbohydrate. Right? It's an aldehyde group. Red peptide is formed. that confirms the presence of the aldehyde group. Another test now. If this is further oxidized with the nitric acid, both this aldehyde get converted to carboxylic acid. Secondary alcohol is not affected, but last one, this is a primary alcohol that is all converted to carboxylic acid. This compound is called as a glucaric acid. This indicate that I have 5 OH group. One of them is a primary alcohol and remaining 4 are secondary alcohol. This indicate that out of this 5 OH group, one is the primary alcohol and the 4 are primary are is secondary alcohol. Right. I hope it's very clear now. So that's how we have proved the molecule of glucose molecule, the structure that we have discussed till now. Any doubt, ask me now. Anmol, Neha, everyone? No doubt? Yes, right? Okay. All right. Now again sharing my screen with you. When we are representing here the linear straight chain structure of the glucose, there are some examples which prove that it is not a straight chain. It has some cyclic structure. Now I am giving some evidence against the straight chain. Earlier I have proved that the structure, but now I am proving that straight chain structure is not possible, right? Or the presence of the aldehyde is again doubtful. Let us see this one. The glucose, we have proved that it is aldehyde group, right? And the property of the aldehyde group is that it can react with sodium bisulfite and give an addition product. It gives here ONA here and SO3H, right? It should give. But the molecule of the glucose does not show this test. Does not show this test, even though the molecule contain aldehyde group. It means the aldehyde group is present, but still it's not showing its presence in this reaction. It means I have a doubt that the glucose may not be present there. May not be present there, right? Another glucose molecule or any aldehyde molecule that is a aldehyde, it react with ammonia NH3, right? And it form here C, then OH here, and then we have an NH2. Right? It forms this, but the glucose molecule do not give this test. The remaining part of glucose is in there. I'm drawing the whole structure here. The glucose, it does not react with glucose. Wherever we have a carbonyl group, we have studied in the chapter of the aldehyde ketone that it reacts with a 2,4-DNP test, 2,4-dinitrophenyl test. NO2 here and NO2 here. From here, we can remove water from here and we can get here N, then NH, then we have an NO2 and NO2, right? So that should give me the reddish brown PPT. That should give me reddish brown PPT, precipitate. But glucose does not give this test. Even though glucose molecule, we have proved earlier that it has aldehyde group. It shows the tolerance region test. It shows the ethyl test. It react with the HCN. It react with the hydroxylamine. It shows the presence of the aldehyde. But these are the three reactions which indicate that the molecule or the glucose does not have aldehyde group. Got it? Now, another. I have discussed the structure of the glucose, right? One structure of glucose. But when we analyze the glucose structure, we analyzed that we have two types of glucose. One is alpha D glucose. Two types. Another we have called it the beta D glucose. Both have different boiling point. Both have different optical rotation. Both have different boiling point and different. The boiling point, sorry, not the boiling point, melting point. Melting point of alpha D glucose is 419 Kelvin and beta D glucose is 423 Kelvin. And from the optical rotation point of view, this alpha D is plus 11 degrees, right? And here alpha D is 19.2 degrees, right? It means their optical rotation is different. The plane polarized light, both of these are dextrorotatory, but their optical rotation is different. But the optical rotation is different. Am I clear? Alpha D glucose and beta D glucose. I hope it's very clear. So how come this? How come this? Now it was not proved by the structure that I have explained. Next point is, if I have an alpha D glucose, D plus glucose, right? Plus here stand for that it is dextrorotatory, and its specific rotation is a positive 111 degrees. Other I have is beta D plus glucose. Here this alpha D comes out to be positive 19.2. If I make a solution and read and leave it for some time, after some time we find the rotation is 52.5 degrees. It means what is happening is we get the equilibrium mixture. Some part of the alpha is converting into beta, or beta is converting into alpha. Right? Alpha is converted to beta and beta is converted to alpha. It is now mixture 52.5 degrees. 52.5 degrees. It is coming in between the two. Right? This interconversion of alpha into beta, beta into alpha, this is called as a muta rotation. It's called as a muta rotation. It's called as a beta muta rotation. Right? All this could not be proved by that straight chain structure. Then a cyclic structure was proposed. And then we had to prove how disequilibrium is also there. Let us see to it. Before I go ahead, let me know, is that all clear to everyone? Till now, everything is clear. Right, Neha? Ashwin, Pravin, Ashmat, everyone? Right, yes, read. Okay, perfect. Now, I'll discuss about the cyclic structure of the glucose. One, two, three, four, five. I'm drawing the straight chain structure first. Now understand that here, one, two, three, four, five, six. For the fifth carbon atom, the electromagnetic effect this side and H goes with this, and this O negative makes bond with the carbon. With this, what will happen here? One, two, three, four, five, and six. Between 1 and 5, there will be cyclic structure and oxygen will come in between. And this oxygen now gains the hydrogen from the fifth carbon atom. It becomes OH here. It is now OH here. Like this. This gets converted. Or it may possible that this OH group now comes on the this side from between 1 and 5. 1, 2, 3, 4, 5. Rest is all same. Rest is all same, exactly same, no change at all. Only what you find here is the OH group on the left hand side here and right hand side here. When it is on the right hand side, it is called the alpha D plus glucose. And this is called as the beta D plus glucose. Alpha D glucose and beta D glucose. Understood now? Now I have two forms and these are all interconvertible into each other. Right? Now, another point now. The structure that I have drawn here, the structure that I have drawn here, to explain the chemical properties, we will not be drawing so big structure every time. So what we have done is we have compressed structure. We have compressed the structure to the another form. We call it is a Fisher projection formula. Let us go to the Fisher projection formula now. What we have done, we have to draw a 6-membered ring and oxygen here. This is the C1, C2, C3, C4, C5. On the C1 position, see here on the C1 position, I have here 1, 2, 3, 4, 5 and 6 is oxygen here. Whatever the groups present on the right hand side, They have to be shown below the plane, and those which are shown here on the right and left hand side, that will be shown above the plane. It means on the C1 position, OH down, H up. OH down and H up. On the third, it is the OH up, H down. On the third, it is the OH down and H up. Then H down and it is CH2OH. H here and CH2OH. This is how we compress the structure. All those H or OH which are toward the right hand side, they have to be placed below the plane, and those which are towards the left hand side, they are to be shown above the plane. This representation, OH below, it's showing that it is the alpha D plus glucose molecule. And in the beta D glucose, only one change will be observed, that is the OH will come above here, beta D plus glucose. So that's how we can represent the structure like this. Am I clear to you? Am I clear how to represent the structure of the molecule of the glucose, how to convert the straight chain into the cyclic form, and cyclic form into the Fisher projection formula. Right. Now we'll discuss about the structure of the fructose. Coming to the fructose. I have shown you the structure of the fructose like this: 1, 2, 3, 4, 5, and 6. It's a ketonic group here. CH2OH. On the third carbon atom, OH group on the left hand side. And now I'm going to number it: 1, 2, 3, 4, 5, and 6. One possibility, what I find here is that the electromagnetic effect here, and from the sixth carbon atom, the H goes to this. So what I find here on the second carbon atom, it's 3, 4, 5, and 6. Between second and the sixth, there is one oxygen. One oxygen. And this OH group may be on the right hand side, and the C1 position goes like this. Rest all are H and OH. OH this side on the third carbon atom. And the other structure, 1, 2, 3, 4, 5, 5. 6 is here. Like this. Now CH2OH this side and OH this side. Rest all are H and OH, nothing else. Everything same. This is called the alpha D fructose. And this is called the beta D fructose. If the OH group is toward the left hand side, it is called the beta, and on this side, right hand side, it is called alpha. Right. And now we can convert into Fisher projection formula like this. All those atom group of atom which are on the right hand side, that will be shown below the plane, and which are towards the left hand side will be shown above the plane. Right. Howard's projection formula. We call it the Howard's projection formula. We call them as Howard's projection formula. Any doubt with the structure of the fructose now? Let me know. Glucose and fructose, two structures are clear. Straight chain structure that was rejected, and then we converted to the cyclic form, and cyclic converted back to the Howard projection formula. So you should be able to draw the structures and understand the structures. Till now, any doubt? Rinad, Vipin? Done. Let us go ahead. Okay. Then we have another structure. Now talking about the disaccharide. Monosaccharide we have done. Now talking about the disaccharide. In the disaccharides, those disaccharides are those carbohydrates which upon hydrolysis give give two monosaccharides. For example, if I say sucrose, upon hydrolysis, it gives glucose and fructose. Maltose gives glucose and glucose, means two molecular glucose. We have a lactose, it'll give glucose and galactose. So disaccharides are those carbohydrates which upon hydrolysis give two monosaccharides. Right. So I'll be going step by step. First, I'm going to discuss about the sucrose. Sucrose is C12H22O11. This has a specific rotation of 66.5 degrees. When dissolved in HCl, means basically we're doing the hydrolysis, it gives C6H12O6 and C6H12O6. This is a D plus glucose, and this gives a positive 52.5 degrees specific rotation. And this is the D minus fructose. Glucose upon hydrolysis gives glucose and fructose. It's 92.4 degrees. Right? Just give me a second, please. Now, so you can see that the sucrose is dextrorotatory. You can see it says dextrorotatory. And this is also dextro. Fructose is levo, but levo magnitude is more. Levo magnitude is more. Right? So there is a change in the optical rotation, and this type of sugar is called as the invert sugar. Right? And this reaction is called as an inversion reaction. And this reaction is called as a inversion reaction. This reaction is called as a inversion reaction. Am I clear? Now, let us go to the structure part of it. Structure of glucose. This glucose is consist of D glucose. Just a minute. Right. So it is a D glucose and beta D fructose. Right. The two molecules are joined together by the alpha D glucose and beta D glucose. Let us go to the beta D fructose. This is a glucose molecule, alpha D glucose. Alpha D glucose. And the second molecule is beta D fructose. It is like this now. It is a C1 here, CH2OH, OH down, H up, H up, and this is a CH2OH. From here the water goes out. And the two molecules are now joined with each other. Draw the structure. And H up and OH down. This has got combined here, O here. Now it has got like this. It's a oxygen here, H and CH2OH. It is a CH2 here. This linkage between the two units is called the glycosidic linkage. It's called the glycosidic linkage. This is the structure of the glucose. Sorry, sucrose. Understood? Now I'm drawing the structure of maltose. About the maltose, I said the maltose upon hydrolysis gives two molecules of the glucose. So now two alpha D glucose units join together like this. It is oxygen here. Draw the structure of the first of all alpha D glucose. And from here the two molecules goes out. Means water molecule goes out, and between two units, C1 of one carbon atom and C4 of another water molecule. Between the two, the condensation process takes place. The water goes out. Rest structure is same. Rest all structure is same. Right. This is called as a glycosidic linkage. This is called as a glycosidic linkage. Right. This is structure of the lacto about the maltose. Now we talk about the lactose. Lactose consists of two units. One is the beta D galactose, beta D galactose, and beta D glucose. Let us see now. This is the first of all galactose. Beta. Beta means the OH will be up here. And the fourth carbon atom also, the OH is up. The difference between the glucose and the fructose is in the galactose is C1, 2, 3. 3 and 4, both the OH group are on the upper side. OH here, H and CH2OH. And now remove water from here, and between two units, I just joined it. Rest all is same, just joining. And this is the structure of the lactose. Understood? Okay. And now these are all disaccharides. And now talking about the polysaccharides. First of all, in the polysaccharide, I'm discussing about starch with a molecular formula C6H10O5 N times. Just a minute, please. Okay, polysaccharides. Starch is one example here. Starch formula is C6H10O5 N times, right? This gives maltose, sorry, upon hydrolysis, if we go for the hydrolysis, first of all, it gives maltose here, and then it gives the D-glucose. It means the glucose units are joined together to give the starch. From the hydrolysis only we can find out, from the hydrolysis only we can find out that starch is made up of some glucose units. Now, starch is made up of two components, right? When starch is made up of the two components. One is called the amylose, other is called the amylopectin. Amylose and amylopectin. So this amylose and amylopectin, 15 to 20% amylose and 80 to 85% amylopectin, they form collectively the starch. It's a mixture of amylose and amylopectin. Now let us discuss the structure of the amylose and amylopectin separately. So first of all, amylose. Amylose is a polymer of roughly 200 to 1000 alpha D glucose joined together with the C1 of the one molecule and C4 of the another molecule. It goes like this. Suppose I say I have a one molecule here, another molecule, another molecule. I have 200 to 1000 such units, H, OH, OHH, and so on. From here, the water goes out, and they form like this, right? So rest all combination of the alpha D glucose are same, no change. So such type of units which are joined to a linear chain, that is called the amylose. Am I clear? The rest attachments are same, no change at all. With H and OH, H and OH, they are same. This is the structure of the amylose. And now I'll discuss about the structure of the amylopectin. Collectively, it will give starch. So let us go to the amylopectin. Before I go ahead, let me know, is that all clear to everyone? Vipin, Asmith? Okay, right. A thread. Good, Jakir. Okay. Now let us go to the amylopectin. Amylopectin. Amylopectin is also a polymer of alpha D glucose straight chain, but at certain point it is linking through the C1 and C4. Let us see. I'll tell you C1 and C4 and C1 and C4. Let us see. This is the one molecule here, and it is joined with the another unit. So many, large number, right? Large number are there. Roughly 100 to 20 to 30 such units joined together. It is joining with the C1 of the one and C4 of the another one. But now C1, C4, then C1 with the C6 of the another molecule. Now see the let us see the next molecule here. Here we have a CH2OH. They link joined here, right? And so on. It is joining with the long chain here. It is joining with the long chain here, continuation. But at certain point, C1 and C6 combination takes place here. C1 and C6. And this branch structure that we get over here is called the amylopectin. 85% amylopectin, 15% amylose collectively will give you starch. Collectively will give you starch. Understood? Till now, any doubt? No, Jakir. I will say long chain C1, C4, C1, C4, and at the some point C1, C6. That branch structure will give you the amylopectin. Right, Zakir? I'll show you once again. See, C1, C4, it's a long chain. Then C1, C4, C1, C4 here also. But between the two different chains, there is a interrelation, there's checking in between the C1 and C6. This is called as the amylopectin. This is called as the amylopectin. Right now. Now all clear now? Okay. So it was all about the structures of the carbohydrates. All about the structure of carbohydrates. In this chapter, we have to study the structures only. And now we can discuss about some functions also, right? Functions of carbohydrate. For a living system, carbohydrates are very important because they are the source of energy, right? The source of energy. They become the part of the body in the form of the starch, cellulose of the plants, right? Otherwise, if it consume it in the form of the sucrose or glucose or fructose, they are the part of our energy. They are stored in our body in the form of the glycogen, right? They are the raw material for many other products in the human body. So that's all about the proper functions also, right? Basically, it's a part of the energy. They're energy giving components. So with this, the carbohydrate is over, and now we can start the proteins. Now I can start with the proteins. What are proteins now? Write down. Proteins are high molecular mass. Proteins are high molecular mass. Complex biomolecules of polymers of alpha amino acid. Polymers of alpha amino acid. Complex biomolecules of polymers of alpha amino acids. Right? Polymers of alpha amino acids. So first of all, we discuss about what are these amino acid and what is the meaning of the alpha amino acid. As the name indicate, it should have not two component. One is the NH2 group, other the carboxylic acid. Next carbon atom is here, and on the alpha carbon atom, I have an NH2 group, and here it can be any R, any long chain, any branch chain, any cyclic, any benzene. This is called as a alpha amino acid. The two components here. One is the alpha amino acid, amino and NH2. Amino group at the alpha position of the carboxylic acid, so we call them as an alpha amino acid. Any doubt till now? Alpha amino acids. These alpha amino acids, if you see them in 3D structure, NH2 away, right? It's a carboxylic acid. It's a H. It can be any other R group. You can see this is a chiral carbon atom. And if you make its mirror image, if it dextro, the other will be levo. Other will be levo. Dextro and levo. These are the two non-superimposable mirror images. These are called as a dextro and a levo. Right. Now let us come to the nomenclature of it, of amino acids. Here I have two groups. One is the NH2 group, right? And this NH2 group is capable of donating a pair of electron. So I can say this group is basic in nature. And the other part is capable of donating the H positive ion. So I can say this is acidic in nature. Acidic and basic. Acidic and basic. Acidic are those, right, which can give the H positive ion. So if if the it contains more NH2 group, the amino acid is categorized as a basic amino acid. If you have a more number of carboxylic acid, that will be called as an acidic amino acid. And if it contains equal number of NH2 and COH, it is called the neutral amino acid. It is called an alpha neutral amino acid, depending upon the number of the NH2 group and number of the carboxylic acid. Number of the carboxylic acid, number of the, right? Then it is further classified as essential and non-essential. Essential amino acids are those which are not synthesized in human body. They have to be taken in our diet, right? They're called as alpha amino acid. And non-essential amino acids are those non-essential amino acids are those which are not which are synthesized in the body by itself. We may take in our body or we may not take in our body. Doesn't matter, right? If we take in our meal, in our food, that will be additional. Otherwise, if we, even if we don't take it in our food, then there will be no any malnutrition disease due to lack of them because the body synthesizes it. But if essential amino acids are missing in our food, that will cause a malnutrition disease. That may cause some malnutrition disease. Got it now? Alpha amino acids and essential amino acids and non-essential amino acids. Am I clear till now? Write in the chat. All clear? Right, acid. Okay, Jakir. Ashwin, Asmat, Pipin, are you getting this? This chapter is like biochemistry. It talks about the molecules of life, right? It has some relation with the biology, but we are not studying biology at all. We are studying the chemistry. We are studying the biochemistry of the biological system. So we call this as a biochemistry, right? Um, Normally, people, students are afraid of this chapter. Those who are from the non-medical background, they say that they'll have to study the biology, but no need to after get any terror from this chapter, right? It's only chemistry. It is not mathematics. It is not biology at all. Right? It is just chemistry. But yes, of course, we're talking about those molecules which are present in the human body. Now, we discuss about physical properties of we discuss about physical properties of alpha amino acid. Now, look at the structure of this amino acid. I want to ask a very simple question from this. What do you conclude from the structure? Is it a ionic compound or it is a covalent compound? You have to tell me. It is an ionic compound or it is a covalent compound. Write in the chat box. Oh, I want to see, I want to know your conclusion. The structure that you're seeing or you might have drawn now, the structure of amino acids, is that a covalent compound or it's an ionic compound? Just one word, covalent ionic. What do you think? Write in the chat, message box. A thread says ionic. Okay. Praveen, Vipin, Jakir says covalent compound. Okay. Renat, Fatima, Neha. Okay, A thread. If you can turn on your mic and tell me how you have come to this conclusion that it is an ionic compound. How you have come to this conclusion that it is an ionic compound.
Because the compound consisted of ions, the plus and minus ions in this bitter ionic form. So I thought it was ionic.
Where is the positive and negative ion? Can you show that? Can you tell me where is the ionic compound? Where the ions are there? Positive and negative ions are there. I'm sharing my screen. You tell me. Keep on look at the structure and tell me where is the positive and negative in this structure. I have not drawn any positive or negative charge here, and I have drawn the sharing of electrons. It's a covalent compounds. So how have you come to this conclusion that it is a ionic compound? Yes, yes, right. Actually, your answer is right, but I want your justification. No idea? No idea? I want to see your chat. No idea. Zakir, how do you say that it is a covalent compound? No idea? Okay, let me now tell you if you're not telling me anything. If you look at the structure that I have drawn, it seems to be covalent. And if it is a covalent, it should have low melting point. It should be amorphous. It should not be soluble in water. But practically, we find it's a crystalline solid. It's a very high melting point, just like ionic compound. This indicates that the molecule must be ionic. But here, from the structure, I find that it is not ionic at all. But the properties show it that it is right. So, how do you prove it now? We can prove it like this. This is acidic. It can give the H positive ion. It is taken up by the NH3 group here. It become now NH3 positive, CHR, and COO negative ion. With this, what will happen? With this, what will happen? It will acquire positive and negative charges. If it acquires positive and negative charges, it's an ionic compound. In the same molecule, positive and negative ions coexist and it is called as a zwitterine. The same word I have explained in the chapter of the amines also. So between two such units, The negative and the positive ion interaction will be there, and it will be purely electrostatic. In that case, in that case, what will happen then? In that case, what will happen? It will be like an ionic compound that will have a high melting point, that will have a high boiling point, that will be soluble in water, right? So we say that these amino acid exist as zwitterion. They exist as zwitterion. Understood? And now we talk about these amino acids. We're talking about just structure like this NH2CH without any changes here. This R is different. This R is different. All right. So we have 20 different amino acids in all the biological world. Till now, we have found that in all the plants, animals, then microorganisms, bacteria, virus, everything, we have 20 different amino acids. 20 different amino acids. These are different. It can be hydrogen. If I put here the hydrogen, it will be NH2, CH2, COH. In that case, we call this is a glycine. If you put here CH and CH3 here, then we call this is a alanine. Right. Similarly, if I keep on changing the groups here, I will have 20 different amino acids. Right. In nature, we have found that we have 20 different amino acids. Now let us go to next part of it. I'll now discuss about isoelectric point of amino acids. Isoelectric point of amino acid. First of all, I'm drawing the structure of the amino acid in the form of their zwitterion form. So this zwitterion, if we add here H positive, NH3, CHR, COH, and then go back in the basic medium, right? This H will attack upon this. In the acidic medium, if you're passing current, it is positively charged and that will move towards a negative in the acidic medium. But in the basic medium, suppose we add here the OH ion over here, that will take out the H positive from the NH3 and that will make it an NH2, CHR, and then become COO negative. Again, back to this. It is now negatively charged and that will move toward the positive. In the acidic medium, in the basic medium, they are moving towards different electrodes. They're moving towards different electrodes. There is certain pH at which movement will not take place either toward the cathode or toward the anode. That pH is called as the isoelectric point. For different amino acids, for different amino acids, we have different isoelectric point. Right? For different amino acids, we have different isoelectric point. I hope you understand the meaning of the word isoelectric point now. Understand? Let me know. Yes, everyone. Okay. I had discussed about the zwitterine, the existence of the amino acid as a zwitterine. They are not covalent, they are ionic. And because of their ionic character, they have a high melting point, high boiling point. They are soluble in water. They have electrostatic force or attraction. They move towards the electrodes. They show the electrophoresis. Right? This all shows that these are ionic in nature. And that I have proved it. That I have proved it. Right? And now, next is the proteins now. These proteins are polymers of amino acids of alpha amino acid. It is one amino acid. I'm drawing the another structure now. It's a second amino acid. Right? Between these two molecules, remove water molecule. And this bond formed between the two molecules is called the peptide bond. It's called as a peptide bond. It's called as a peptide bond. The bond formed between the two amino acid is called as a peptide bond. If such type of large number of amino acid join together, right, you can join from this side and then can join from this side, right, you can keep on joining, then what will you find? What will you find? You will get a long chain of the amino acid, and we call this is a polypeptide. We call this is a polypeptide. And when the molecular mass of the polypeptide becomes greater than 10,000 atomic mass unit, becomes greater than 10,000 atomic mass unit, it is now called as a protein. It is now called as a proteins. It is now called as a proteins. If the molecular mass exceed 10,000 atomic mass unit, it is called as a protein. If it is less than 10,000 units, it is simply called as a polypeptide. Understood? Any doubt till now? Let's take up this case now. First of all, I say I have a glycine, CH2, CH, CS3, right? And now from here, you can see that I have made a protein like this, right? This part is obtained from the alanine, this part is obtained from the glycine, and this part is obtained from the phenylalanine. In between, I have removed the water, phenylalanine. You can see from here I have removed, if I put up here the OH group over here, from the H here, the water is gone. Put here the OH group here and the H here and remove the water. That I have removed. And after that I'm getting, after this I'm getting, it is a 3 monomer units joined together, and I'm getting here 2 peptide bond here, one here and one here. Right? 2 peptide bonds here, but the 3 units are joining, so we call this is a tripeptide. It is called a tripeptide. Right? It can be alaglyphy. I say alaglyphy. Alaglyphy means alanine, glycine, phenylalanine. It can be randomly joined in different ways. I have joined here as a alanine, glycine, and phenylalanine. But if I join in the random way, I have different possibilities. Let us talk about the possibility. It can be what I have drawn here as a glyalaphy. It can be glyphyala. Got it now? Glycine, phenylalanine, and alanine. Then I put the alanine here. Ella glyphy or Ella phi gly. Or I can put here the phi as in the beginning here. Phi gly ala, or it can be phi ala gly. So different combinations are possible, right? And these all different combinations are responsible for different functions of a organism. Suppose I am giving one example that this sequence, this triplet code is responsible for for the um, for the skin texture, skin color, right? Skin color. All of us have a slightly different skin color, right? Some are more fair, some are light fair, some are little bit dark, some maybe whitish, some maybe right different skin colors are there. The sequence of the proteins and the skin are different, and that is why they have a different skin color or skin texture. The protein structure is different, right? So we cannot change that structure. We cannot change the structure by using some chemical, by using some creams or some beauty products, right? All the beauty products are fake from this chemistry point of view, right? The basic color of the skin cannot be changed. Yes, you can make them clean. That is another aspect. Yes. You can make them clean, you can make them shine, that is possible. But you cannot bring the dark color to the fair color, right? That what you find, you might have seen uh, an advertisement of Fair and Lovely, right? Different beauty products, that your skin color will come from a dark color to the bright color. That is all fake. The protein is structure. The proteins cannot be changed. You can make them wash. You can make them like clean. You can make them like shine, right? But you can't change the color. So for different sequencing, and the different people have a different sequencing, right? So they have a different color. Got it? Interesting? Yes or no? Understood? All of you? So this much we have done the protein, beginning of the protein, right? And then in our next class, I'll be discussing the classification of proteins and their reaction of the proteins, importance of the proteins, and then go to the next part, nucleic acid, in our next class, right? So that's all for today. I'm ending the session now, and now see you next week. Okay, then. Goodbye for now.